Hello everyone, Mr. Fawcett here, and we are back with another Algebra 1 lesson. Today we're going to be talking about literal equations. So we've worked our way up from one step to two step to multi-step, talked about equations with fractions, equations with decimals, all those inverse operations, the combining like terms, and even the equations with infinite and zero solutions. So again, today's just one more type. I mentioned before, by the end of this course, one of our goals is for you to be able to solve any type of equation that's acceptable for someone who leaves Algebra 1 to have knowledge about, which means that we need to cover quite a bit. So today's just another step in our journey. We are going to talk about literal equations. So let's jump right in. It says Jessica drew a non-square rectangle on a piece of paper. So what I want you to do is pause the video and try to write an equation for the perimeter of the rectangle. So you're not given any actual lengths. You just have the sides labeled as L for length and W for width. So try to write the equation for perimeter, and maybe there's more than one way to write it. So do your best and then come back here and see what we have. Okay, so perimeter, if we remember, is the sum of all the sides of a figure. So with a rectangle, we have four sides that we have to add together. So length plus width equals perimeter. And you could have those sides flipped. You could have P equals W plus L plus L. You could have these in whatever order you wanted to, as long as you had all four of them there. But is there a different way to write this equation other than just switching the order of the L's and the W's? Well, there is, right? If we have L plus L, that is equal to 2L. And if we have W plus W, that's equal to 2W, which is equal to P. So we have one way, we have two ways, and believe it or not, there's actually one more. We haven't talked about it yet in this course. Maybe you've been introduced to it in a pre-algebra course, maybe in your middle school math courses. But what we could do is factor this 2 from both the L and the W term. So another way we could write this is 2 times the quantity L plus W is equal to P. So there is our third equation for perimeter. Now, this equation didn't have a ton of numbers. One of the equations, the red one, didn't have any numbers in it. It just had variables. And this is what a literal equation is. It's an equation made up of many letters. You can have some numbers in there, but most of the things or the terms in there are going to be made up of letters rather than numbers. So that's what we're going to fill in down here. Literal equations are equations that are expressed in letters. These letters can either represent variables or numbers. Now you may ask, well, how could a letter represent a number? Well, there are special letters that we have in math that just stand for certain numbers. So for instance, we have letters like the Greek letter pi, right? That's approximately 3.114. Oops, let's make that one a little better. It's approximately 3.14. Some other letters you may not have heard of yet are the letter E. That's approximately equal to 2.7. And there's some other ones that stand for other numbers. Basically, it's an easier way of writing that number, right? Because pi is an irrational number. Its decimal goes on forever. So if we had to try to write out the decimal, right, we'd either have to cut it off at some point, or we would have to keep writing it, and we would never get through the problem because we'd be writing the decimals of pi forever. So sometimes we use letters to stand in for certain numbers because it's more efficient for us. I want you to try to come up with some other equations that contain mainly letters. So think back to your pre-algebra or middle school curriculum, and specifically I would look at other area and other volume equations. So maybe you had the area of a circle, the area of a square, the area of a triangle, or the volume of a cube, the volume of a cylinder, etc. See if you can remember what some of those formulas were, because the majority of those formulas, well, they're made up of letters, right? And not very many numbers. So pause the video, see if you can come up with any other equations, and then we'll review some together. Okay, let's clear this and let's come up with some. All right, so one equation would be the formula for the area of a triangle. So we'd have area equals 1/2 base times height. Again, that's the area formula for a triangle. We have the area formula for a square. So the area equals one of the sides squared, right? Because a square it's really length times width, but for a square, the length and the width are the same. Let's do some volume formulas. So we have the volume of a cylinder. So volume equals pi r squared times h, or pi times the radius squared times the height. One of the more familiar ones to you may be the volume of a rectangular prism, which would just be length times width times height. Maybe we have the area of a circle, one more area formula, pi times the radius squared. Maybe we have some physics formulas. Maybe you remembered something. You haven't taken physics yet, but you will, and you'll see an equation that looks like, let me number this other one first. That was number 5. Let's do number 6. You may see an equation like force equals mass times acceleration. Maybe you'll see something where we have velocity is equal to the distance divided by time. And there's many others. But one thing that these equations all share, right, if we look at our paper, there's very few letters here. I see a 1/2, and that's it, right? So in 7 of these equations, the only number we had was a 1/2. So again, literal equations, they're equations that just are made up of a lot of letters. And while they may look a little intimidating to work with at first, we use the same concepts to manipulate these equations as we did with our regular one-step, two-step, multi-step equations. So we're going to look at the next page, and Harry has chosen to manipulate this equation right here. So he was asked to get g by itself, right? A lot of times we're asked to get x by itself or to get y by itself. Well, in this case, they told Harry to solve for g. So look at his steps. He made a mistake somewhere. See if you can find that mistake. Okay, that's step number 1. See if you can find Harry's mistake. Number 2 is redo the problem yourself and correct his mistake. So find the mistake, redo the problem to correct it, and then we'll talk about how you did. Okay, so if we look through Harry's solution, the first thing he did was he wrote down the original equation. That seems okay. He copied it down correctly. The next thing he did was multiply both sides by 2. So he didn't write this out, right? But he probably put parentheses around both sides and multiplied by 2. These two simplified, so he was left with 6g plus f right here, which is good, and h times 2 is 2h. Okay, so that step is a-okay. The next step, he said he divided both sides by 6. Okay, I assume that was because he wanted to simplify this g, right? He wanted to get, simplify the 6. He wanted to get the g by itself. So did he divide both sides by 6? Well, he certainly divided, oops, I need my pen, not my eraser. He certainly divided this term by 6, and he divided this term by 6. But what about the f? right? If you divide both sides by 6, you have to divide every single term by 6. So this, going from this step to this step, was where he made his mistake. Okay, so we need to go and try to correct that. Well, I'm going to start off where he left off. So he had 6g plus f is equal to 2h. Now, if you divide by 6, I'm going to divide each term by 6. So I'm going to get g plus f divided by 6 is equal to 2h divided by 6. Now you could certainly simplify 2h divided by 6. 2 over 6 simplifies to 1/3, which is what he actually did in his last step here. But that being said, let's try to get g by itself. So if I come up here, actually, I'll put the work down here. So I'm going to subtract f. Oops, what's going on here? Let's try this one more time. So I'm going to subtract f divided by 6 from both sides. So these are going to simplify. I'm going to be left with g is equal to 2h divided by 6 minus f divided by 6. Fortunately, these fractions already have the same denominator, so I can just subtract the numerators, and I get g is equal to 2h minus f divided by 6. Okay, so now we have gotten g by itself. Notice that we don't really have a number answer here, right? We just have 2h minus f all over 6, but we did the job, right? We got g by itself, and that's what we're going to be doing when we have literal equations. We're just going to be trying to get one of the variables by itself, and the other side may have a bunch of other variables with it, right? Because there's no way for us to get rid of them. Okay, I do want to show you one more way we could have done this. I think it's a little easier way than I did this the first time. Let's go back to what I put down originally. So let's go back to the mistake. Okay, and instead of dividing by 6 first, and you know, Harry may not have made this mistake if he chose to do a different inverse operation first. I think it'd be easier to subtract f from both sides. So if I subtract f from both sides, I'm going to be left with 6g equals, the f simplify, 2h minus f. Now I can just divide both sides by 6, divide the whole thing by 6, and the 6's simplify on the g side, so I'm left with g is equal to 2h minus f all over 6, which is what we got before. Now, you may think the first way was easier, you may think this way is easier. It's up to you either way, because both ways we did it were logically sound mathematically, so we're okay. It's just really your personal preference. Okay, let's answer one question, and then we will do some practice problems. Or maybe we'll save them for a part 2. Well, we may save them for a part 2, actually, because we're already at 15 minutes. So number 2 says, how is solving the equation v plus 4z equals x for z, so trying to get z by itself, similar to solving the equation 3x plus 5 equals negative 16 for x? So in both equations, we are trying to get a variable by itself. In the first equation, we're trying to solve for z. In the second equation, we're trying to solve for x. So take a minute, write down what's similar, and then maybe also write down what's different about those equations. Okay, so I already wrote down the thoughts just so we don't have to spend time doing that, but now we can discuss. So I said we need to use inverse operations for both equations. Right? We need to use inverse operations in the first one to get z by itself. We've got to move the v to the other side. We've got to figure out a way to simplify the 4 next to the z. But we also have to use inverse operations for the second equation to get the x by itself. The idea is the same. The only difference is we may be performing those inverse operations on more so letters than numbers in the first equation. And then in the second equation, we're dealing more so with numbers. But inverse operations, they don't, the way we use them is no different when we have letters or numbers. They work the same way, right? If we need to move something that's negative, we're going to add, regardless of whether it's a variable or whether it's a number. So just because you see more letters, don't let that trip you up. Don't let that make you think this equation is going to be harder. I need to do anything different. Just think about, okay, I need to move this term, regardless of whether this term's a letter or a number. What inverse operation do I need to use to move it to the other side or to simplify it? Okay, we are going to stop there, and we will come back for a part 2 where we'll go over some additional practice problems. So enjoy the rest of your day. I look forward to seeing you next time.